over there. Okay. Thank you very much again, and it's all yours now.
Thank you. I should probably share my screen. Let's see. Oh yeah, I can just grab the screen share. All right. Well, thanks a lot, everyone, for being here. It's a pleasure to be here. One question I wanted to ask just before I get started. Something I've learned from online teaching is that if I'm just speaking at myself at a computer, I end up just like rambling, getting lost in my thoughts. So if any of those of you who kind of have the video here are able to put your video on, I see on the panelist, that would be super helpful. Then, so I know that I'm speaking to at least one person. Thank you. Thanks. So anyways, today I want to talk about machine learning and causal inference, and specifically about how you can use machine learning to do useful causal inference. Depending on what academic scientific community you come from, this might seem kind of like a weird thing to want to do. I've definitely gotten some weird looks because I think the associations between these terms are causal inference. It's about being serious. It's about really measuring the effect of an intervention very carefully. Many communities, causal inference is what you get out of randomized trials. Anything else is kind of more speculative. So there's really this kind of association with rigor. On the other hand, machine learning, right? It's prediction, it's heuristics, it's give it your best shot, and does it really work? Well, let's just try it out. So these are the associations. And I've really kind of sometimes gone to say speak at some like big medical meetings, and people are like, you work on machine learning and causal inference? They're like, that is incorrect. Like, get away from me. But anyways, my goal today is to convince you that, of course, kind of somehow a naive application of machine learning to causal inference could be really bad. But there is a way to pair methods aimed targeted at both problems, and to kind of use machine learning to actually do causal inference that's not just rigorous, but actually maybe more rigorous than kind of standard stuff you could get out of a classical parametric model. So, all right, just to get everyone on the same page, I wanted to talk a little bit about an application I spent some time working on last year. This is from medicine, not the social sciences, but the structure of the problems we face kind of in different communities are remarkably similar. So here the question was, this is data collected by a consortium of first responders in the Paris region in France. And what they were interested in, there's this treatment called tranexamic acid. There's a belief that if you have people who are suffering from hemorrhagic shock and first responders administer tranexamic acid, this helps. But they wanted to do an observational study to get more insight here. So they have data on 3,168 patients. This is not a randomized trial. These are just patients that the first responders actually reached. Some of them were treated with tranexamic acid, some of them weren't. And the question was, did tranexamic acid help? And what makes this data set interesting is that for each patient, we observe a bunch of stuff, not just the treatment and outcome, but also 244 other covariates, including were they in cardiac arrest, what was their hemoglobin concentration, Glasgow Coma Scale, and so forth. So, okay, what are we gonna do? I think the first thing anyone would do here, right, is you build a 2x2 table. Were they treated or not? Did they survive or not? And if you look at this table, it looks like the treatment is very hurtful, right? Among the treated people, almost half the people died, whereas that is not true among those who weren't treated. But of course, we all know what's going on here, right? There's confounding bias. People who were kind of more severe cases were more likely to be treated than others. And if you don't adjust for that, then kind of you don't measure a causal effect. So what are we gonna do? We should go back to these 244 other covariates we had access to. And the hope is that if kind of by looking at who's in cardiac arrest, what your hemoglobin concentration is and so forth, you can kind of figure out people's baseline risk of having kind of dying, then it could also help you disentangle the causal effect. I get a chat, we can't see the slides. It's only the intro slide. Can the rest of you see slides? That would. Can you see me change slides now? Okay, so this was the stuff you had, and this was the 2x2 table, which if you couldn't see, I can see how that would be very, very confusing. So this is the 2x2 table we want to fix. Okay, how are we going to do that? Well, I think the thing everyone's going to do, or kind of really the standard across many different fields, is you're going to run linear regression. So we have a bunch of other stuff. We're going to call them X's. So here X includes your coma scale measurements, hemoglobin concentration, and so forth. Y is your outcome. W is your treatment. We're going to run a linear regression model where we predict Y from treatment and other covariates. And then there's going to be this thing tau, the treatment coefficient. And this is going to be, we're going to estimate this, use this as our treatment effect estimate. And does this work? Well, of course, as always, under assumptions. And what are the assumptions? I think we all know them. One, you had some confounders, but that X need to kind of, in fact, be all the confounders. There are no unmeasured confounders. Once you measure your X's, your treatment is as good as random. Two, for this to be justified, the treatment effect needs to be constant. Right, you're modeling the treatment effect as constant. If it's not constant, then the linear model is not what's going on. And third, you have these measured confounders xi, they need to have a linear effect on y. Again, this is not surprising. It's like baked into the form, right? You assume that if you increase xi by some amount, then y will increase by beta. So what do we think about these assumptions? I mean, these are things you can talk about a lot. One, no unmeasured confounders, right? This is something that you go to a social science seminar, like people will fight about. I think everyone understands that it's kind of your identifying assumptions. If you have it, it's great. If you don't, you need to do something completely different, collect more data. So, right, it's a real assumption. It's expensive, but it gets you a lot. Number two, the treatment effect being constant. Do we believe it or not? I don't know. I'm willing to kind of grant it. Maybe that's kind of a first order modeling assumption. You're not interested in heterogeneity yet, so why not? But the thing I have a hard time with, honestly, is this third one. You had a bunch of X's, and you're somehow assuming that the X's have a linear effect on Y. But at this point, this seems kind of like completely, like, first, I've never seen a seminar where people actually try to justify this assumption. They're just like, control linear, it'll be fine. And second, if pushed, it's very hard to kind of argue that anyone believes in this assumption. Here, for one, remember, this was data collected by first responders. The first responders measure a bunch of stuff. They choose what they measure. They also choose whether to administer treatment or not. So at least there's a story for why unmeasured confounders would work. But what about linear effect? Remember, one of the covariates was hemoglobin concentration. I'm pretty sure hemoglobin concentration doesn't have a linear effect on any health outcome, because probably there's like a good region, and if your hemoglobin concentration is too high or too low, it's bad. So three, it's very hard to find anyone who believes in it or will fight for it. So why do we do it? I don't think there's generally much pushback that there's no scientific motivation for assuming that the confounders enter linearly into the specification. But what people will say is like, look, we've got to do something. We have linear regression. Linear regression puts the confounders in the model linearly. So if we want to use linear regression, then we've got to do it. And again, the goal of this talk is to try to convince you that actually, no, there isn't a strong methodological motivation either for assuming that the X is entered linearly into the specification. There's a way of using machine learning tools right in this problem that kind of lets you get rid of that assumption at essentially no cost. So yeah, again, I'm not critiquing assuming no unmeasured confounders or a constant treatment effect. Like, those are the scientist's prerogative. All I'm doing is trying to avoid making linear assumptions in a part of the problem where literally no one is even arguing that they're actually linearity holds. So that's kind of the high-level goal. It's about using how you can. It's about how you can use machine learning to do rigorous causal inference without making extraneous modeling assumptions. Most of what I'm going to say today goes back to work by Jamie Robbins, Mark Vanderlaan, Viktor Chernozikov, a bunch of others. And I'll mainly focus on basic results from this line of work. In the second half, I'll also talk about some newer results on treatment heterogeneity that are joined with Susan Athey, Cinquendi, and Juri Tefshrani. Yeah, any questions before I get started? All right, so okay, so we want to get rid of the assumption that the x's have a linear effect on the outcomes. In terms of modeling, this is very easy to do. Where before we said that x affects y through this linear relationship, x beta. Now let's just replace x beta by some generic function f of x. Once we write this functional form, we no longer assume that x has a linear effect on y. That's easy. Now, of course, you have to estimate this model. And this seems a lot harder now that you have this unspecified unknown function f in there instead of a parameter vector beta. So what are we going to do? It turns out there's this key transformation you need to do. So here's just a couple lines of algebra. First, what we're going to do is we're going to define the propensity score. The propensity score always shows up in observational study methods. So this is E of x. It's the probability of being treated, conditional on equivariance x, or equivalent to expectation of w given x. And then we're going to define another function that's also important, even though it's not quite as commonly discussed as the propensity score. This is your best kind of prediction of the outcome marginalizing over treatment. So this is the expectation of y given x, but without knowledge of w. So this can be m of x, it's f of x, the baseline, plus tau times the probability that you get treated. And kind of given this formalism, given this notation, you can subtract m of x from both sides. And now what you end up is y minus m of x is tau times w minus e of x plus noise, where the noise is mean zero conditional stuff. I also wanted to note here, I'm doing everything in this kind of modeling framework. You can do everything in potential outcomes notation, and that's what we do in the papers. Here, I just wanted to kind of say one side of notation. So that's why I'm just assuming that the noise means zero conditional on x and w. The potential outcomes analysis takes you to the same place. But so then the end result is that now you can identify this constant treatment effect parameter tau, essentially via univariate regression. Tau is the thing that predicts the residuals y minus m, that is the residual of your best prediction of y before knowledge of w, in terms of the treatment residual w minus e. This is a nice characterization of tau, and it kind of suggests a simple algorithm for estimating tau. What we're going to do is, okay, remember tau was characterized by this regression of y minus m on w minus e, but in reality, we actually don't know. We might know the propensity score, we might not. We certainly don't know m of x, the baseline function. So what we're going to do is we're first going to use all the data to learn the propensity score e of x, learn the kind of marginal response function m of x, and then once we have estimates e hat of x and m hat of x, then we can estimate tau by residual on residual regression. So we're going to plug in m hat and e hat into this relationship that characterizes tau, and then we're going to run that regression. And that's going to be an estimator. Hopefully, you can see where this is going in a machine learning direction. Now, this is a 3-step algorithm, but step 1 was just a prediction problem. Step 2 was just a prediction problem. Step 3 was a closed form manipulation. And now steps 1 and 2, what prediction method are you going to use? Well, just the best prediction method you can find. It could be a deep net, it could be boosting, it could be a forest. You're the expert, right? So this is how machine learning is going to come. But okay, where this thing estimator, it seems reasonable. I think it wouldn't be surprising to argue that something like this should be, say, consistent in large samples if E hat and M hat are consistent. Where this gets really cool is that this actually has very, very nice asymptotic properties. And the key result is something like this. I should mention that in the literature, there's like a huge number of results of this type. This is kind of not the strongest, but it's the simplest to state and the most general. So that's the one I'm using today. Remember in steps 1 and 2, we had to start by estimating the propensity score E of x and the marginal response function M of x. I'm going to assume that you did so using any method, and all I'm going to ask of you is that you're reasonably accurate. So your root mean squared error for M hat of x and E hat of x should decay as 4th root n. If these were parametric methods, well specified, then your error would decay as 1 over square root of n. So I'm allowing you need to be consistent at a reasonably fast rate, but you can be an order of magnitude slower in convergence than a parametric method. And if this is true, then under regularity conditions, you get a central limit theorem for the treatment effect parameter tau. The central limit theorem means 0, unbiased, asymptotically, with errors that go to 0 as 1 over square root n at the parametric rate. And you can check that the variance V is essentially kind of the optimal thing you could have hoped for here. So it's kind of this amazing result where it's a 3-step algorithm. In the beginning, you feel like you're just doing anything, you're predicting, all you're asking is that you need to be in the ballpark of doing something reasonable. And then out you get this central limit theorem that you can use to build confidence intervals that's kind of as good as anything you could have hoped for. Here, I put under modest regularity conditions, so you might be worried about that. But essentially, you can avoid making that assumption at all if you do something like, you do this thing called cross-fitting. It's like cross-validation. When you want to estimate the propensity score, kind of when you plug in a propensity score here, you should estimate it over here. And when you plug it in over here, you should estimate it over here. So if you do cross-fitting, you can avoid regularity conditions, and then you just get this. And again, I guess by now in econometrics, a lot of people are so used to seeing results like this that you can be like, oh yeah, that's cool. They call it double machine learning in econometrics. Different communities call it different things. But I remember when I first started, I was like, this is amazing. There's the kind of, I feel like often there's this garbage in, garbage out principle in data analysis. So if your whole analysis is only as strong as the weakest step in the analysis. And here now you do steps 1 and 2 where you kind of fit the machine learning method to M and E. You try to do a pretty good job, but it's not perfect, and you get 4th root rates of convergence. Then how is it possible that in the last step you get square root rates? You can win an order of magnitude. But kind of mathematically, what happens is that the errors of M hat and E hat cancel out to first order. And this is what kind of allows this phenomenon, but I thought it was pretty cool. Okay, a final question some people ask about this method is like, okay, sure, it's cool, but it's still kind of complicated. It's a 3-step method, like linear regression was just one function call. But again, I might say linear regression is just one function call because you happen to have that function call on your machine. But to those of you who have taken kind of PhD classes on kind of linear modeling in econometrics, one characterization of linear regression you might remember is if you were fitting a linear model of y on x and w, and we call the coefficient of w tau, then an algorithm for getting this coefficient is you first fit a linear model, a pilot linear model to predict treatment from x's. Then you fit another linear model to predict outcome from x's ignoring treatment. You take the residuals of both of these regressions and you regress them against each other. It's exactly the same algorithm we were doing before. So again, this kind of residual regression with machine learning used in steps 1 and 2, it's really just the same thing as linear regression, except in steps 1 and 2, we use flexible methods instead of linear model. So really, it's not that different. It's just, all it's really trying to say is that you had something you cared about W, you had other stuff you didn't care about X, and you just wanted to control for. And this kind of a partial linear model, what it lets you do is it kind of lets you use the same kind of reasoning as you would have with linear regression, but without actually assuming a linear functional form on how the confounders enter the system. So anyways, so that's the thing. So we've talked about estimating the effect of a treatment on an outcome under selection under no one measured confounders assumption. So we assumed no one measured confounders, and we assumed that the treatment effect was constant. And the typical way to do this is to run linear regression of y on w on the confounders, but this actually needs a third assumption still. That's that the x's have a linear effect on y. But actually, that's an extraneous assumption. You don't need that. If you're willing to kind of bring machine learning to the table, you can instead work with a machine with a partially linear model. And then you can replace assuming this linear specification with just an assumption that you have a predictive model that you can use to estimate M and E to reasonable accuracy. And then you can get tau at parametric rates. All right, so these are very well-known results, but just wanted to share because I think they're very exciting. Are there any questions at this point before I move to talking about treatment heterogeneity?
There is one question in the chat section. I'm sorry. Can you able to see that, or just would you?
Let's see. Do I? Oh yes.
Okay.
Oh, thanks. How robust is E hat and M hat? It might be very sensitive to the selections of X. So again, with the caveat that there are many formal, like there's a pretty big sub-community that's working on figuring out what is the best result of this type you can give. But kind of at the level of this high-level result that I've given here, what matters is that you have some estimator, M hat, E hat, and that they converge at 4/3 rates. Now, how robust are those? It essentially depends on what predictor you chose to use. If you're using kind of some very fickle machine learning methods, it's plausible that things would be quite unstable. But if you use kind of something simpler like a forest, then things are probably pretty stable. So it kind of, what this result does is it kind of puts the onus on the analyst to just did a good predictive model, and it's kind of your job to figure out, are you getting something that converges fast enough or not? And then once you have that, then once you have that, then the central limit theorem follows. I'm just realizing there might be another way to understand this question, where kind of what x's do you use here? Throughout this result, I'm always assuming that there's a set of x's, and that kind of you have subject matter expertise you can use to assert that there is no unmeasured confounding once you condition on these x's. So here the x's aren't chosen for modeling purposes. It's just M of x is the expectation of y given x. That's just a definition. The x's are the set of variables required to assume to get unconfoundedness. And then your job is to fit M of x. All right. The question is the result uniform or pointwise, and can we build honest confidence intervals with tau? So first here, tau is just a single parameter. So in this case, the result is, right, this is just a one-dimensional result. There are variants of this kind of thing. Say Dr. Chernozikov has a line of papers where he does this kind of stuff, but you have a bunch of things you're trying to do inference on at the same time. So you can get uniform results, but the result I have here is just a single parameter tau and that kind of thing. In terms of confidence intervals, this is something I should have mentioned. Remember what this estimator is essentially, you just have this y minus m is equal to tau times w minus e plus noise. What we're going to do is we're going to plug in cross-fitted estimates m hat and e hat, and then just estimate tau by this regression. And what this theorem gives you, it actually gives you a little bit more. In order to get confidence intervals for tau, you can actually just run your favorite heteroscedasticity or robust inference method in this regression while pretending that M and E would be the true values of estimates, and you'd get the correct variance. So really the result is that once you plug reasonably accurate M hats and E hats here, you can do all the analysis you'd want in this regression while pretending like the M hat and E hat were the true ones, even though they're actually estimates. And in practice, that's kind of, in software packages distribute, like that's how we do confidence intervals for this kind of parameter. And in my experience, it works quite well. Any more questions at this point? All right. Well, in that case, sorry. Okay. Well, in that case, let's keep going. So far, we've talked about constant treatment effects, but of course, in many applications, that's not all we want. Say, if you're doing personalized medicine, you might believe that there are some therapies that help most patients, but maybe the therapies help some patients more than others. And then you want to use that information for targeting. And if you want to do this kind of thing, then obviously you can't just reduce yourself to a case where the treatment effects are constant, but you need to allow for heterogeneity. And so how are we going to do this? Again, from a modeling perspective, the answer is quite clear. Before we just put in a constant treatment effect parameter tau in there. Now, if we believe that there are covariates that also modulate treatment effects, then you can just make the treatment effects tau of x be a function of x. So now there's heterogeneity in the treatment effects. Our statistical task just got harder. We're not just estimating a single number tau anymore. We're estimating a tau of x function. But we can still try to do this. And now we're going to just get ourselves oriented. Let's say x were discrete. So kind of you could cut your space up into pieces and then tau were constant inside each piece. Then we'd already know what to do. First, chop your space up into pieces and then use the constant treatment effect estimator we talked about in the first half, and that's going to work well. Where this is going to be challenging, of course, is that x might be continuous, x might be high dimensional, and then we're going to need to do some kind of smoothing across similar values of x in order to get a handle on this tau of x function. And this is going to take a little more work. So how best to do that is our next topic. Okay, here's again the comment about potential outcomes. You can do all this with potential outcomes also. You just need a little more notation. So now, before talking about kind of one solution that I think is promising, I'm first going to talk about something that seems deceptively promising, but that I do not recommend. And it's the following. Under the model from the previous slide, that is that the y is kind of a baseline effect plus w times tau of x plus noise that's mean zero conditional on x and w. You can check that tau of x is equal to mu1 of x minus mu0 of x, where mu1 of x is the expectation of y given x for the treated, and mu0 of x is the expectation of y given x for the controls. Okay. This formula here, tau of x equals mu1 of x minus mu0 of x, it's just true. It's a consequence of unconfoundedness. But now, how are we going to turn this into kind of an actionable estimation strategy? Someone might say, okay, mu1 of x, it's just the expectation of y given x on the treated. So what I'm going to do is I'm going to focus on the treated units, learn to predict y from x, and get mu1 of x there. Similarly, I'm going to focus on the controls, fit y from x on those, and get mu hat 0 from x there. Then I have mu hat 1 of x, mu hat 0 of x. Those are just prediction problems. I know how to solve them. And then I'm going to estimate tau hat as mu hat 1 of x minus mu hat 0 of x. And I'm done. How could this possibly go wrong? If we know that tau of x is literally equal to mu1 of x minus mu0 of x, So if you have good estimates of mu1 of x and mu0 of x, then can't you just take the difference of these good estimates and you'll get a good estimate tau hat of x? But it unfortunately doesn't work this way. There are many things that could go wrong. I think this picture from paper by Causal et al. Is particularly nice because it just really highlights how this can go wrong in just a very simple setting. So here we're in 1 dimension. So x is 1-dimensional. On the y-axis, you see the outcome. Red x's are controls. Blue dots are treated. Blue dots are treated. And then we're going to start, remember, by fitting a predictive model. So we're going to focus on the controls, fit y from x, on the treated, fit y from x, and then take the difference. And so what happens? Well, we start with the controls, and we have a lot of red x's. So now we're going to deploy some good piecewise linear modeling tool on this task. It's going to correctly find that there are some spots where the shape of the red surface changes, and it kind of correctly fits a flat area and finds a bump and then goes down. And you got a very good estimate mu hat 0 of x because you had a lot of data. Now we're going to go look at the treated. Well, there are actually very few treated units here. So again, you're using a very good piecewise linear predictive method that here correctly notices there's actually not enough data to find a bump. So you're just going to push a blue line through this and you're done. You have a very good estimate mu hat 0 of x, and you actually have a very good estimate mu hat 1 of x, where your method appropriately noticed that there wasn't enough data to do anything complicated, so it just did something simple. But now remember, tau hat of x is mu hat 1 of x minus mu hat 0 of x, and what happens when you take the difference? You start with a big treatment effect, then suddenly near the bump, you end up with a small treatment effect, and then you again get a big treatment effect near the end. And even though kind of by eye, there's obviously no treatment heterogeneity here, just the fact that you had more data on the controls than the treated units creates an artifact where you think there's a lot of treatment heterogeneity. And I guess this is kind of like a cardinal sin in statistics where you find heterogeneity where there is none. This is really not good. And I'm sure you can imagine situations where it can be just kind of practically terrible if just like amounts of data on treated versus control kind of systematically biases your treatment estimates. So we don't like that. So what can you do instead? The claim is that, again, we know what to do, right? In the first half of the talk, we figured out kind of a method for estimating constant treatment effects that we liked. That is, run residual, estimate m hat and e hat, and then run residual regression. Now, what is estimating treatment heterogeneity? It's nothing but, right, kind of finding groups of people who are similar. And then once you've found groups of people who are similar, then just estimate a constant treatment effect over that group. Again, this is kind of oversimplified. You need to smooth, but that's the high level intuition. If I gave you some specific point x at which I wanted to estimate a treatment effect, one very natural way to do this is kind of find a neighborhood around x over which kind of we expect treatment effects to be representative of tau of x, and then just apply residual regression in that neighborhood. And the question is, so kind of this formula here, tau of x is residual regression over the neighborhood, that we already understand. The remaining question is just how do we smooth over x's? How do we pick a neighborhood that's representative for this at this point tau of x? And here there are many choices. A classical approach might be to use something like K-nearest neighbors or Gaussian kernel averaging to define these neighborhoods. Here instead, I'll talk about a different approach that uses random forests to get a notion of these neighborhoods over which we then can apply residual regression. All right. So this is just why random forest is kind of somewhere on the spectrum from simple to complicated. But it's simple enough that it's easy to understand what's going on, but already adds a lot of value over something classical like K-nearest neighbors. So, okay, where we want to get to is talking about how can we use a random forest to guide a notion of neighborhood search for applying residual and residual regression to estimate tau of x. But before doing that, I just want to quickly review what is a random forest in the basic prediction setting, so we're kind of all on the same page there. So for the next few slides, let's switch gears. Instead of there being an x, a y, and a w, there's just an x and a y, and all we want to do, this is the basic machine learning task, we want to predict y from x. And how are we going to do that? Well, there are many methods. You could do k-nearest neighbors. And what is k-nearest neighbors? If you want to estimate mu of x, that is the expectation of y given x, you draw a circle around x. You look at all the data points you have that fall inside that circle, you take their average, and you estimate mu hat of x is just the average of the y's inside that circle. What is a forest? Well, kind of to understand forests, we first need to talk about single trees. And what is a tree? Well, it's the same thing as k-nearest neighbors, except instead of averaging data inside a circle, you average data inside a rectangle where the rectangle was chosen to kind of represent the data well. So here, your prediction mu hat of x from a tree would be you just take a rectangle, look at everyone who falls inside, and take the average. That's your prediction. In 2 dimensions, these pictures, you might say, they just look the same. What's the point of using a tree over k-nearest neighbors? And in 2 dimensions, there really isn't much point. Where there's a point is that when you go to, like, say, 20 dimensions, because the curse of dimensionality, in order to draw a ball in 20 dimensions around a point x that contains any data at all, the ball has to be huge, and then you're going to get a very poorly represented neighborhood. Whereas trees can kind of focus and have like narrow splits on features that matter, but kind of longer splits on features that don't matter. And they can gain a lot of power that way. So what's special about trees is how they pick their notions of neighborhood. And here, the way they do so specifically goes back to 1980s, the CART algorithm. The idea is how you're going to grow a tree is recursively. So you start by putting all your data in a single blob, and then you're going to try to split your data in 2 halves. So you're going to make an axis-aligned split, and then you're going to imagine fitting a very simple model. On this side of the split, you predict one average, and on this other side of the split, you predict a different average. And then you're just going to kind of try to pick the split where this kind of simple 2-parameter model gets the lowest mean squared error. This is kind of by expanding the square, equivalent to picking the split that maximizes the weighted difference, number of people on the left times number of people on the right times the difference in the averages to the left and the right square. So you do that once, that's one split. And then what trees do is they recurse. You split it once, now you have data here. Now you kind of start again. You can imagine splitting this in half and this in half. This recursive structure is super heuristic, but it makes the algorithm very easy to run. And it works surprisingly nice. So that's a single tree. What's a forest? Well, the problem in growing trees is that often you might worry about, hey, you chose a split this way, but maybe you could have chosen a split this way, and it's almost as good. And why did you pick this split instead of this split? Why do you pick this split instead of that split? And the idea in forests is, I think the community in the 90s spent a lot of time trying to choose between trees and figure out what's the best tree. And in the end, they were just like, look, don't choose between the trees. Just grow all the trees that are kind of plausible and let the random forest be the consensus average prediction of all the trees. So that's the thing. So you grow a bunch of trees, you take their average. And then once people notice this, they actually got excited and they tried to like figure out ways to make trees more and more different. And so you can average kind of from a greater diversity of trees possible. And the way you could do this is by kind of training trees on different subsets of your data and randomizing variable selection choice. So once you do all that, you get a bunch of different trees, you average their prediction. That's a random forest. When you kind of go talk to people at a tech company and they're using random forest for all kinds of different kind of routine prediction tasks, this is what they're doing. This question, this is like multi-threshold models. I mean, there are many ways to think about trees. Different communities have their different favorite ways of thinking about trees. My favorite way to think about trees is that it's like k-nearest neighbors, except where you kind of ran this recursive algorithm to choose what your neighborhood is instead of drawing a circle around the point. But yes, I mean, algorithmically, you recursively threshold data. It's a very simple data structure. So there are many ways to think about it. So, okay, this is for prediction. What we want to do is use this for treatment effect estimation by residual regression. And here you might think that this is kind of a little bit weird for two reasons. First, we wanted a neighborhood we could use for residual regression, and a forest doesn't really look like a neighborhood. It looks like an average of trees. It's very algorithmic. And the second thing is you might think what I'm going to say is we're going to have a bunch of trees, and each tree is going to estimate the treatment effect, and then we're going to take an average of these treatment effect estimates. And you might be worried, saying like, look, if you have a treatment effect estimate that's unstable, you could like end up doing something like dividing by 0. You could get a couple of trees that just make very bad predictions, and they're going to ruin the whole forest. So we don't really want to do that either. So this might seem kind of like a tricky spot, but it turns out to make progress, it's very easy once you just apply a simple transformation to the forest. Typically, we think about a forest as an average of tree predictions. But if you look at what this means that you take an average over capital B trees over the prediction of the tree, and the prediction of the tree is just an average over your n samples of yi, your outcome, times an indicator, did the observation xi fall into the leaf containing B, divided by the size of the leaf. Okay, so that's a tree. And when you represent it kind of like this in terms of more primitive terms, you notice that a forest is just a double sum. And now what you can do is you can permute the double sum, and you see that the forest is actually just a sum over the training examples I to n of yi times this thing alpha ix that essentially measures how often is the ith training example in the leaf containing x. So a random forest is a weighted average of the outcomes yi with weights alpha ix. So the picture is essentially this, right? A tree is just a weighted average of outcomes where the weight, each observation gets like weight 1 over leaf size if you're in the leaf and 0 otherwise. And what the forest is, it takes kind of all these weighting functions from individual trees, and it averages these weighting functions. And then it's a weighted average of the yi's with these averaged weighting functions. So you can, from this perspective, this is numerically equivalent to a regression forest, but it's a pretty different perspective. Regression forests are now adaptively weighted estimators where your adaptive weighting function comes from kind of averaging the weighting functions from individual trees. But the thing is, kind of once we did this, it's kind of clear how to make progress. We wanted to estimate treatment effects over a neighborhood. We wanted to do so via residual regression. And all we had to do anymore is kind of define a neighborhood over which to run this. Now, if we run a forest, the forest actually gives us a weighting function for each test point x. It gives us a set of weights alpha ix that kind of define in a kind of soft way the neighborhood of training examples that are relevant to estimating an effect at x. So now what are we going to do to estimate tau of x? We're just going to run residual regression. So in a preliminary step, we had already estimated m hat of x and e hat of x to predict y and w from x. We're going to take residuals, and then we're going to run residual regression, but kind of to estimate a treatment effect on the whole sample, a constant treatment effect, we would have just run this regression. Now we want to focus at x, and we assume treatment heterogeneity, so we're just going to do a weighted linear regression instead. We're going to ix these weights alpha ix to focus the estimation in the neighborhood of x. And this is going to give us the parameter, an estimate of the conditional average treatment effect at X. So anyways, this is kind of at a high level how you get estimates of heterogeneous treatment effects out of a forest. There are, of course, a bunch of other questions here that, I mean, I could talk for an hour about just kind of details about how to do this kind of thing. For example, I think the biggest thing is once you're in the mindset of you want to train a forest to estimate heterogeneous treatment effects as opposed to make predictions, well, the natural difference is, remember, a random forest, it's kind of an average of tree kernels, where in the regression case, the trees were grown to express heterogeneity in the conditional response function. They were kind of built to predict y from x. Now, if we want to get a forest that can be used to express treatment heterogeneity, you need to figure out how do you build trees that split to express treatment heterogeneity as opposed to outcome heterogeneity. So how are we going to do this? Well, we're going to, again, proceed greedily. So we're going to follow the blueprint of the Bryman's cart algorithm. We're going to start with all our data. We're going to want to split it in half. And then for each split, what we're going to imagine is we're going to imagine kind of fitting a treatment effect parameter on one side, fitting a treatment effect parameter on the other side. And then we just follow the blueprint from before. For each split, we kind of, the quality of the split is measured by kind of how many people are on the left times how many people are on the right times the difference in treatment effect estimates to the left and to the right squared. You pick the split that maximizes difference. And then how are we going to estimate tau hat L, tau hat R, that is the treatment effect estimate to the left and the right? Well, the answer is, again, residual and residual regression. So we're going to run residual and residual regression to the left, to the right, pick the maximum difference, and split on that. So again, I realize that there's a lot of stuff here to digest, and I'm going quite fast at this point. But really, I promise at the high level, what we did was we just kind of took Bryman's random forest algorithm, and every time Bryman takes an average, we run a residual and residual regression. So that means every time Bryman was targeting the conditional response function, we're targeting the conditional average treatment effect via residual and residual regression, and then you just push it through. I mean, of course, there's like a lot of implementation details to worry about, but if you want to use it, you don't need to worry about it because we worried about it once. So this thing here is an instance of a generalized random forest. The package is on CRAN, so you can use it and you don't need to worry about kind of the computational tricks needed to actually make this strategy feasible and speed it up. Are there any questions at this point? I see one. Do you have references about the treatment heterogeneity case? On my website, I have a bunch of references on this if you're interested. Probably if you want to read about how you use forests in practice, I have a paper with Susan Athey called something like Estimating Treatment Effect with Causal Forests and Application. It's in observational studies that kind of starts with an overview. So that might be there could be a good place to start reading.
Stefan, we have one question and I missed it. I guess it's referring to your earlier slides. I don't know if you can keep it the last minute or.
Let's see.
Q&A, or I can read it to you if you want.
All right, that'd be great. I can't click on the Q&A. Yeah.
So if you predict your model with a deep neural network, is it fine with those conditions of mean square error, which is 1 over n power of 0.5?
Yes.
Yeah, you in the first or the second slide, you show the kind of the condition that's basically related to this one.
Yes, this is a great question. So, do you actually believe in these forth-through rates of convergence? In a parametric setting, right, asking for a forth-through rate of convergence is nothing. In a machine learning setting, it's actually asking quite a bit. So there is kind of, now that kind of this kind of result, the community has recognized that they're very important. Then there's kind of a cottage industry of kind of trying to prove this kind of bound in different settings. So if you want to use the lasso, you're in high dimensions, you have n sample, you have p parameters, you assume that you're sparse, so you only have k non-zero parameters, then you can get this kind of rates of convergence out of the lasso under nice conditions if k is less than square root n over log p. So that's kind of one condition. You need to be pretty sparse, but not kind of ridiculously sparse to get this. For deep nets, there's actually a recent paper out of Chicago Booth where Max Sparrow, Teng Yuan, Liang, and Sandra Misra there who established conditions under which they can check this condition for deep nets. And then, of course, do you believe in these? Like, let's say you actually have like electronic medical records data, or you have like image data, and are you getting force through rates of convergence? It's hard to say, right? But at least that we have some papers showing that kind of under more classical regularity type conditions, you can get this kind of rates out of deep nets. So I think in a way, how should one think about this result? I think that like a classical econometric approach might be, okay, you have this result. So now your next job is to start proving theorems about how fast different methods converge, and do you get force field rates, and kind of the force field rate is the cutoff. And the way I think about this result is more as kind of a type of guidance and intuition. What I like about this result is that it doesn't make any assumptions on m hat and e hat other than that they're accurate under root mean squared error. So what's the implication? If you want to apply this method in practice and you have many candidate machine learning methods, which one should you pick? Well, pick the one that's most accurate in root mean squared error. Is it going to get force field rates? That's harder to say, but at least the one that has the best shot at getting force field rates is the most accurate one. The reason this is super nice is that in kind of machine learning, the thing people are used to evaluating models by is root mean squared error. So this kind of creates an alignment in incentives. That the thing you want out of a good method is exactly what the machine learning people have been focused on for many decades and giving you. That is a method that gives you accuracy under root mean squared error. Now, once you have this alignment in objectives, is this enough? Do you actually get good estimates of tau? I think that in any specific example, it becomes more of an empirical question. Like I said, there are a bunch more formal results here. If you get force field rates, I can guarantee you normality, but you can get kind of close to normality under other conditions too, or you can get normality under the kind of more delicate proofs also. So what I'd kind of recommend is if you actually want to use this in practice, use this to motivate just focusing on accuracy, and then just kind of try it out on realistic synthetic experiments and see, do you believe that you get valid coverage? Another question, if I understand your model correctly, my question is, as the observation in each cell gets smaller when the tree grows, how reliable is the estimate of heterogeneous treatment effect? This is a great question. And here a forest helps you a lot, because you might worry that kind of when you grow trees deeper and deeper, each tree has very small leaves. So then each tree makes very unstable predictions. So how could you possibly get good predictions out of this? But there's something very nice that happens in a forest. It has to do with the averaging across trees. There are some formal results that point to this. I don't think the formal results quite capture like the full extent of the nice stuff that happens. What essentially goes down is trees kind of in the beginning when there's signal and it's kind of clear where to split. The trees are going to split on the signal. Then, but now that you train trees on subsamples, once you kind of pass the signal boundary and it's kind of unclear is there signal or not, trees are going to start splitting on the noise. But every tree you train is going to kind of, because it has access to slightly different data, it's going to look at the noise differently and end up doing something slightly different. So trees kind of behave systematically at the top, but when you go deeper down, their behavior gets very, very chaotic. But then what happens is that the forest actually, it's going to average trees where each tree is kind of badly overfit. But because each kind of tree overfits in different ways, when you average out that, you average out the chaos, and it's almost like if you had just stopped splitting at the level where you no longer had signal. So this kind of averaging out process of the forests is very, very important. And if you actually look empirically, I think trees are things people like in practice because they're so simple. You can print them on a piece of paper. They're very interpretable. But actually, as a predictive method, trees are not particularly accurate. The kind of averaging out phenomenon in a forest is key in order to get trees to work well. Yeah, that's a very good question. Any more questions here? I guess I am pretty much out of time. I have in the slides, I shared the slides with the organizers. So in the slides, I still have an application and I have some discussion about, say, how should you validate methods for treatment heterogeneity and how should you think about deploying something like this, because you probably can't deploy predictions from a black box forest in a sensitive application. I kind of hope that people go with that. But I think, so hopefully the organizers can share slides with everyone if you're interested in that. But I'll probably stop here so I don't go over time and take any remaining questions.
Thank you very much. If you have critical slides to come, I mean, we can put like 10 more minutes. We can ask people. I mean, it's not like a vocational seminar. But if you stop at this point, that would be fine as well. I mean, this is up to you. We can add a couple of, because you answer the questions along the way. So I think you may even spend a couple of more minutes to summarize, wrap up the things if you want.
Okay.
It's up to you.
Okay. Well, I can quickly cover an application then to just get some, and then I'll stop after the application. So here, just to try this out, something validating methods for treatment heterogeneity is often difficult because you can do it in simulations, but in real data, how do you know if you did the right thing or not? It can be kind of tricky. So here's a data set that I thought was nice. It was kind of, I got this from Guido Imbens. This was about evaluating a welfare to work program, the Greater Avenues to Independence study in California. They had a bunch of covariates, and they ran 4 separate randomized studies in 4 counties in California. The way you can turn this into an observational study is you can just smush together the data from the 4 randomized trials. You created confounding that way because the randomization probabilities and the kind of participant mixes weren't the same in the different counties. So now you have machine learning methods can try to work very hard to figure out the propensity score that is essentially based on your covariates, what county were you from. And they can try to do that. But then when we want to evaluate a method, we can kind of bring back information about which randomized study you come from. And we can get kind of very transparent evaluation. So here, there's treatment, that's eligibility for gain. There's outcome, that's kind of income, quarterly extra income, average 9 years post-study. There are 54 covariates we're controlling for and using to model heterogeneity. And you can fit a causal forest here. And you get a shape like this. So you have some people who seem to have responded up to like $200, $250 per quarter extra income from the treatment. Others are below 10. Or others are below 100, I mean. And kind of using the randomized study information, you can check that actually, if you were to split the people based on kind of the people who the causal forest said have a high treatment effect versus low treatment effect, their kind of difference in response is around $80 in quarterly extra income. post-treatment. So this big effect, it's a complicated type of data set. The X's take many forms. There's kind of past income numbers. There are kind of binary things that are like categorical things, say demographics, and the forest can handle that and find some heterogeneity. So that's cool. If the question was, is there heterogeneity in how people respond to welfare to work programs? The answer is yes. But now what are you going to do with this? It's probably kind of hard to imagine using these black box predictions to decide who's eligible for the program and who's not, because it's hard to interpret these decisions. And I guess one thing that's particularly concerning here is if you start looking in, there's data on gender, there's data on race here. And in order to control for confounding, you essentially have to control for race. But now you're like, is the forest splitting on stuff like that? It's obviously not okay from a prioritization point of view or a policy point of view. So that's kind of a difficulty. So what can you do? And just to kind of close, I wanted to talk about kind of briefly, like this highlights that estimating treatment heterogeneity is often of interest. You want to know that some people respond to treatment differently than others, but kind of often it's just the first step in an analysis. And then once you know there's treatment heterogeneity, you want to describe the heterogeneity in an interpretable way. You want to turn the heterogeneity into a simple policy. So there's usually a lot of post-processing work to do. And kind of in the GRF software package, we're building up increasingly many tools for this kind of post-processing. So one thing here we did was, in the setup, you had a forest that kind of tried to predict who's going to benefit the most from the GAIN program or not. And it seemed like this very uninterpretable black box. Then in this efficient policy learning paper with Susan Athey, we talked about, okay, can you post-process what you got out of a forest to learn a simple tree that kind of captures the difference in who benefits from the policy and who doesn't. And when we ran our algorithm, it gave us this thing. First looks where you paid 3 quarters ago. If yes, you treat those who have a high school degree. If no, you treat those with children. Again, is this something you could deploy or not? That's a difficult question, but I think that's not a question statisticians or econometricians should answer. That's a question that kind of subject matter specialists should answer. Hopefully this tree is simple enough that subject matter specialists and stakeholders can talk about it. And then what I can say from a statistical point of view is that in the end, the estimated utility gain from thresholding by this tree obtained by post-processing in the forest is actually, again, around $80 per quarter, average 9 years post-treatment, which was essentially the same gain as you got from thresholding a causal forest. So this showed that kind of what I'm trying to point here is that often if you want to use these methods of treatment heterogeneity in a research project, often the end result is going to be some kind of post-processing of the forest. There are many ways to do so by kind of projections of the treatment effects and so forth, or by trying to come up with a simple policy, where here's one example of that. Okay, I think now I'm really over time, so I'm going to finish here. Just say thank you, everyone.
Thank you very much, and thank you to all our presenters and speakers. It was a very nice and beautiful, great day for today. And if you have a couple of seconds before we leave and end the whole thing, and I'm going to show you the second day. Yes, continue. So I'm going to share this, and then just for the tomorrow. And you see right now it was today, and we updated our website, and all the presentations over here. And then if anybody is missing anything, and if you want to go back again, the presentations, and then you can go that you can click all there, and then you can see the presentations. And soon, after editing, and then we are going to be able to, very soon, but we are going to be able to post the video clips. So for tomorrow, we are going to start again 10 a.m. And we have a very good line of speakers. Stan, Mehmet, Anders, Dario, and Patrick will talk about very interesting topics. And hope to see you all tomorrow as well. Again, thank you very much for your time. And it was a great day. And then you are we are in different countries right now, and Italy, the US, and then Europe, and Anders, I guess, from connecting from somewhere in UK, I guess. Okay, thank you very much again, and it was a great day, and thank you for your time. We really appreciate it. Okay.
Thank you again.
Bye-bye.
Thank you, everybody. See you tomorrow.
Bye-bye. See you.
Bye.
Stop it sharing.
Bye, Arthur. Bye, Mehmet.
Thank you. Bye-bye.
Bye.